Just to make you aware, I have two parts about the compiler, but I don't want to make it very invasive or brain filling. So the second part is much lighter and shorter, so we will have more time for questions and things like this. Also, in case I'm overspilling out of the first part, I would just continue the rest of it into the second. So we have this time a little bit of relaxation. If you remember the agenda, we will have two parts on the compiler, and we will have some time left for at least for questions and a bigger discussion, I think. This content is not run so far. This is not the usual compiler presentation that we have at Intel. Probably you can imagine we have a lot of engineers who like to present you a lot of details. So the standard deck, to make it short, is more than 200 slides just on compiler, vectorization, flex, and examples. So it's probably we die after such a session. So for that reason, I try to collect something that is more meaningful for your case. And the second part is actually entirely a collection of do's and don'ts. No, not really, but more practical things. So you can see the intro or agenda for this talk for the first part. It gives you again some intro on the Intel AVX 512 instruction set extension, but it will also give you the status of the compilers. I said compilers, not just Intel compiler. This includes explicitly the GCC, the GNU compiler collection, as well as the LLVM Clang compiler, and which version you should expect to be okay for AVX 512, and what you can expect in terms of auto-vectorization capabilities, perhaps a little bit about. Then some newer features also on how to actually deal with vectorization in scientific codes. Sometimes you see a lot of codes that just leave out any particular target flex or generating AVX or AVX2 or whatnot. They just rise the optimization level and that's it. And we will see how to deal with, say, regression test failures or reproducibility issues, and how to get vectorization plus reproducible accuracy and some reasonable trust into the vectorization capabilities. Then we will look into the expressing vectorization, and I will leave out a big, very pleasant part, actually covered by a public and available standard like the OpenMP 4.0. I will leave this to my colleague, to Michael Clem, but we'll look into a little bit of an overview of intrinsic programming. I know it's a stretch goal because some of you already do work and go deep into it. Others never heard and probably don't want to touch. But it might be interesting for you at least to look at what is that kind of thing. Everyone talks, or we talk often about it, and what is this about, and how much can you gain from it? And then we will also look into array sections, and some of the topics are not necessarily new, right? Some of them are pretty old if you think about Fortran 90 and array sections, but they are still not used, although they are a good vehicle to do explicit vectorization to some extent at least. And for the OpenMP part, as I said, I just wanted to mention and forward essentially to Michael Clem's talk, which is, and I just forward you the most interesting parts or mention them. This is the loop vectorization and the kernel-based, the SIMD function-based vectorization with OpenMP 4.0. And in the end, I have a little bit of a special topic, like not a gourmet topic, but the small kind of thing on how to get going with intrinsics when you rely on GCC or LLVM, because there is some caveat with dealing practically with these intrinsics. I think I will relieve you from history of instruction set extensions at Intel prior to 2009, but you can see there is a long line of things. I will come back to that, why that is, but let's look at the more recent things like this is pretty outdated, the slide, you can to be done, but we can fill in the number, I guess. For KNL and for Skylake Server, you can see the AVX 512 materialized. And it is not just promotion of vector width or instructions to 512-bit. It is really a kind of a new instruction set, which breaks to some extent with previous AVX. So it's not only a natural extension. We will see what it gives us. First, the motivation here is, why do we want to have, or why do we get all the time new instruction set extensions? The truth here is probably to some extent that hardware innovation happens to a large extent at the ISA level. This is true, I just wrote that down in the smaller print there. This is true for CPU as well as GPUs. You've seen that recently for machine learning. There, the whole domain is now covered by new instructions like half floats and lower precision instructions. And it means the innovation to get better performance for a specific domain wasn't because of something magic. It is actually happening at the instruction level architecture, which is true for CPUs and GPUs. So that is probably something normal, right? If we discover in our hardware-software co-design some gap with an important application, we explore immediately, or we explore the possibility to fill in that gap on the instruction level. And just for terminology, domain-specific versus general, AVX 512 would be some general instruction set extension that allows you to express basically anything you want, not just a specific, say, cryptographic algorithm or accelerating this or that, but it is something that allows you to write scientific applications in general. On the other hand, or that also means that the compiler, or our compiler and others as well, are essentially asked to generate such code regularly based on high-level code. So the goal with a general instruction set extension is to generate that kind of code out of high-level languages like Fortran, C, or C++. It is not the intent to rely on an intrinsic enabling. In contrast to that, domain-specific ISA extensions are often not meant to be covered by any high-level code generation. So there are also examples from the Intel side. You can see they're listed like CRC32 instruction in SSE. Probably there is no idiom recognition in Intel compiler to capture some bit twiddling, which would be better written as a CRC32 instruction. No, you had to always write it explicitly, right? Or use a library that did this for you. And same goes for other cryptographic extensions and maybe other domain-specific extensions. So there are these two kinds of meanings behind instruction set extensions. With AVX 512, as I said, it's not only a promotion from 256 bits to 512, it is actually a rethinking of the instruction set architecture that Intel had, despite of keeping the naming like AVX. It gives you more resources, as we heard earlier from Michael Clem. It gives you 32 registers and wider registers, so it's a big resource increasement, basically. And it also gives you an entirely new architecture on the masking side. So previous architectures, or AVX, for instance, they used regular registers to keep masks around, right? If you wanted to leave out some of the entities in a vector or in a vector, you used another vector like an integer vector to have zeros and ones collected into, but that wasted a lot of space. As you can imagine, for every state, which could be 1 and 0, you just wasted an entire 32-bit integer or something else, right? And there is no need for that, and as the vectors become longer, that becomes more of a problem. So the instruction set actually also introduced additional registers, K registers, to cover masks and things like this, and also unified the instruction set in the sense that all instructions can be masked. It's not just that you have few of them enabled for masking because someone anticipated that that might be useful. The entire variety of all the AVX 512 instructions allows you to use masking. And it is also unified in the sense you might have heard in the past how many operands an instruction has. That is also answered by AVX to some extent, AVX 512. It is always the 3 operands per instruction, right? You heard about FMA 3 versus FMA 4. And in any case, with all AVX 512, it's 3 operands. And in most cases, for almost all instructions, that means you have non-destructive behavior. Just as an explanation, you load the source operands, and you produce a result, an output, and it is fully sufficient to rely on 3 sources essentially. And only some instructions are exceptional that might require more inputs or outputs, which is the case eventually for FMA, which is one exception, because it is also an exception in itself. It is basically 2 instructions in one instruction. It's a multiply and an add fused together, so there is nothing you have to wonder about that this is requiring more than 3 operands. On the other hand, it also means FMA3 is destructive, to just give you some deep dive on that side. Let's look into more and larger registers. You can see this is a natural extension, at least from the naming. You have this Y register set for the 256 wide instructions, and you have the Z registers that just double the width of the registers, and then also give you more general purpose. It's exactly 32 of these 512 registers. And then you have essentially 16 elements per 512-bit vector in single precision, or 8 double precision elements per vector that you can process in one instruction, basically. And it also gives you an idea, why do we want to have instruction set extensions or vector instructions at all? Because you do one instruction rather than 16 or 8. So you have something that we call instruction size reductions. Not that the size of the instruction becomes smaller, that could be also the case, but it also means you have fewer instructions, right? And if you run at the same clock frequency of a processor, and you run you essentially run fewer instructions, there is a potential that you get more work done, right? Because that is the case, the simple motivation for all the vector instructions. And as I said, you have 8 mask registers, K registers, and I think I will give you something more on the compiler status with respect to GCC. I believe, for the top of the head, 4.9 version of GCC introduced the very basic enabling for AVX 512, and 5.2 filled in the gaps. In particular, just to give you this at this point here, I think in the very first shot, the 4.9, the maintainers rejected K register implementation. So none of the intrinsics that are supported in 4.9 allow you to be masked, because the infrastructure in GCC isn't or wasn't there at this point, but this is filled in. So with regular GCC 5.2 and beyond, you can just work with masks as you like. And there are 4 different granularities that you can get. You can see this, you have different mask granularities, but I think this is a detail you can look up yourself. And the motivation is already given with the mask registers. It's basically, it would be a huge hock in the size if you used general purpose registers instead of real bits or only bits for masking things out of a vector, because you can get it in the left upper or lower corner of the previous slide. I will jump back. You've seen you have 16 elements of single precision in such a vector, and now that allows you to just use 32 bits to mask any of the states that you want, right? Rather than wasting a huge register for that. So masking would be useful in general. Right, you can use it for very simplistic control flow things, like deciding about only one thing. Of course, if you decide about 2 things, you can repeat the control flow and just think about making it a masked version again. But in general, you can turn simple control flow into a masked execution if you like. In many cases, this is possible, but it is also useful for remainder handling or loop peeling. Of course, maybe loop peeling is not a good idea. You need to peel until you have a multiple of the vector width and until you are aligned in memory. Then you may run the main part of the loop, which is basically some job that your compiler does for you, and then you eventually have a remainder, and then you have different choices for the remainder. You can do a normal, or you can just do a masked vector operation, or you can also do some scalar loop, which is just using sequential scalar code for the remainder of the loop. And you can see it is a very useful general vehicle that you want. There are, of course, more features in AVX 512, so it's pretty comprehensive. There are embedded broadcasts and masking Embedded means, to give you an idea what an instruction actually is. An instruction is a collection of bits that enables the CPU to actually know what instruction it should execute. You know, on x86, general purpose instructions are varying in size. You heard that against RISC, and you know what that means. But with AVX 512, I think most of the instructions have, in a basic form, they have the unified or a single length or size. But the prefix or the instruction encoding itself can also contain operands. It's not just the case that you need operands always to be registers or from memory, but the instruction set also allows you to embed some of the operands into the instruction itself. It's sometimes useful, sometimes not. We have seen instruction set that just died because of that. The embedded essentially immediates into the instruction, which never scaled beyond, into the next generation of compute requirements. But you can do neat things, like you could, just as an arbitrary top-of-the-head example, you could embed a stride for a load or some address modification for the access. Anyhow, let's look at the picture that we've seen before. As a reminder, there was this baseline, and maybe the question why the foundational F and the CD conflict detection is not one bucket. There's a very simple reason, I think. On the Intel side, we were not sure in the beginning if CD will make it into the processor, right? They collected cases, and then they found it is useful and it is worth doing, and therefore they are essentially available both as foundational on any of the mic or upcoming server parts. But in general, because of that legacy, they got some separate CPU ID bit. This is just the history of it. But on top, you can see the PR instruction set for Knight's Landing, which is prefetches just for gather and scatter. It's pretty exotic, right? Normal prefetch instructions or architectural prefetches on x86 are present independent of AVX 512. You can do prefetches since ages on x86. And you can just use a regular instruction that has been around probably then a decade or longer. And these PR instructions are just prefetches for gather scatter operations. So this is pretty special, I would say. And then you have this ER, which is the transcendental instructions that you can use for logarithmic or exponential functions, and they are essentially meant to be accelerator instructions that help you to do another Newton iteration on top of it, right? If you do, for instance, some square root, you only get, we will see that later on, 28-bit of accuracy out of it, and that doesn't sound really encouraging, but you can do another Newton iteration, and you know it's an exponential convergence, and you can double the number of accurate bits in just one additional iteration. So it's a very good vehicle, essentially, to accelerate higher order functions. I will skip over this. Sorry, excuse me. Let me step back. We have some special, or we have one demonstration tomorrow on LAMPS, an application actually, that gives you some insight on how to use conflict detection instructions. So this is a highly optimized atomistic simulation that uses some of these instructions to accelerate neighbor list processing in some many-body problems or three-body problems. There is some summary on that, of course. I think you're already aware of it. A reminder on something we heard earlier about turbo and the relationship to AVX 512. I think this slide is from General Xeon Line Classic, but it's the same for KNL, and we heard about turbo bins, that we have a nominal frequency, a turbo frequency, which is entirely opportunistic, and then we have a down bin essentially for heavy instructions like energy-hungry instructions like AVX, and you can see this in the number of marketing buckets introduced for the main line. You have a rated base frequency, you have the turbo, you have the AVX base, and of course the same turbo bin on top of it. This applies, and you can see how that applies in terms of actual numbers. We've seen that. We've seen this table early on in Michael Clem's presentation, I think. Just as a reminder, why I'm saying this is, if you expect in the best case a 2x improvement over 256-bit wide instructions, vector instructions, it's not really true. You also have instruction size reduction, so the number of instructions may go down by just using AVX 512, but maybe a good, but still a lucky assumption would be 2x in performance, right, out of AVX 512, and sometimes you can't see it. And it's because of these instructions are rated higher in energy consumption, and the frequency of the core will eventually drop because of that. So sometimes that makes the difference, right? You actually utilize the 512 nicely, but because of that, the frequency goes a little bit down, and then you get some reasonable thing. But the idea behind these turbo buckets and frequency scaling and so forth is to leave out or to leave some advantage at all for your code, of course. That is the whole purpose. Otherwise, you wouldn't need to do it. So how to use that? This is what I mentioned or promised you to do. Give you a status on the compiler side. You can see compiler code generation, which to some extent means also auto-vectorization. That means idiom recognition. It recognizes access patterns, loop structures, and things like this, and generates vector code by itself. This is probably, I don't want to make any disclaimers on that, but I think it's best with Intel compiler to have, if you want a bet for auto-vectorization, I think maybe Gray compiler is also good. I haven't tried it, but probably it's better at least than, say, the GNU compiler collection or maybe LLVM. But intrinsic level is all equal, right? This is the same. At that level, you can express the similar things between the compilers. And you can see that for Intel compiler, you have buckets or essentially common names or collections of flags. So you have something called common AVX, which only uses the instruction set present across KNL or Mike and the Skylake core. And you have some core AVX for the Skylake server part, which enables essentially underneath a dedicated set of instructions that are generated out of code generation. For GNU compiler and LLVM, you have that much more explicit, but it doesn't exclude that you will get buckets later on. I know that LLVM already did it, and GNU did it for AVX2. For GNU, you can say -m core AVX2. Which is a true Intel name, right? Core architecture is on the Intel side, and it means you get an umbrella of flags that are dedicated towards core AVX2. And the same may exist for AVX 512 with Skylake flavor and Mike flavor. But so far, I think reliable across the first version with AVX 512, you can rely on this collection of things. For the common set, I highlighted MFMA. The unfortunate thing is you could say, oh, well, AVX 512 today should include FMA. We have that since more than a decade, right? And it might include FMA instruction generation, but it's not true. You need to enable that separately. And if you don't, you just, as a theoretical peak, you are sitting at half the performance, right? To make that clear. So this is a very important flag. On GCC and LLVM, you need MFMA, otherwise you don't get FMA instructions. No fused multiply add, half peak performance only. And then you can have the throw common set, which is F and CD. And then you can go for core AVX Skylake core and add these four guys. And on KNL, you can add these 2 guys if you want. LLVM luckily adopted the same set of flags, very same name, nothing special. And then there is something else on top of it. Given the case you want to do intrinsics, say you want to do intrinsics. The funny thing is Gray compiler, Intel compiler, unhappily, or also Microsoft compiler, to your surprise, they allow you to write intrinsics without enabling the compiler flag for that particular instruction set architecture. So if you write an intrinsic which belongs to AVX2, You don't need to add AVX2 flag to the compile line on this mentioned compiler, practically Intel. But on GCC and LLVM, unluckily, you need this collection of flags. Otherwise, you end up with something terrible you don't want to have, I guess. You need to add these target flags. And I will have this very last session in this talk goes about how to relieve and relax and do something about it, because it's very inconvenient, right? I will give you some examples for it. To summarize from what you heard about AVX, as a scientist, you probably want to make sure that your make or build system uses a target flag at all, right? This is very simplistic, but I try to make it not so invasive, right? So hopefully you get something out of it, because performance has two components on any of these compilers. It is basically the optimization flag, which is nothing about the target architecture, and the target flags. You need these two guys, otherwise you won't see any vectorization or good performance out of it. So you want to say O2 or O3, it's your choice, whatever safe is for your application, and then you want to say, oh, generate AVX2 code or AVX 512. Okay, just a warning, I think this is true for LLVM as well. The O2 flag is basically a collection, it's an umbrella flag, which means a whole set of flags again underneath of it. For O2 with GCC, you need a flag that enables vectorization, because I think O3 is the first optimization level that includes vectorization on GCC. So if you really want to adopt GCC instead of Intel compiler for whatever reason, you can learn something from these previous slides. Numerical reproducibility. So this is an important topic for many of you if you work on an actual application. Because if you add, say, AVX2 code generation and say O2, just to be conservative, you might end up with regression failures or reproducibility issues or incorrect results, supposedly incorrect, right? Who knows what is correct with scalar versus vector code, but you could say this is an incorrect result. And what can you do? On the Intel side, you can choose, this is a very neat way, you can choose FP model precise for the C++ code. In average, I think the geomean across the spec benchmark suite, it gives only about 10% slowdown. And it permits, or actually depermits, certain optimizations, right? So it gets clear what optimizations are meant by that, because if you look at the Fortran side, the corresponding flag is not really precise. Maybe it is now available, but I think Fortran compiler didn't implement precise. They always had something called source, which is basically what you see is what you get. If you write an expression with braces, you get the expression or code generated according to the bracing, right? If you say multiplication first because of bracing, or addition first, you get it this way. And with that flag, you can make that happen for the Intel Fortran command. There's the question.
I think that's the default behavior on GCC. So you assume that floating point operations are not commutative.
That's true. That might be true. So the assumption for the floating point model on the Intel side, I think O2 and O3, I'm not sure, is fast 1. There are two levels of fast. There is FP model fast equals 1. If you don't write equals 1, it means equals 1 by default. And there is a fast equals 2, which means relax more. Do more of these unwanted or potentially incorrect expression modifications, right? You can reorder and things like this just to make better code. And with precise, to summarize from that, is really you can make sure that that won't happen and gives you some baseline of accuracy. As a practical example, I've vectorized the CP2K application always without FP model specification in the past. And I got hundreds out of thousands regression tests. I got hundreds of misses or failures. With FP model precise, I'm just at the same level as the scalar code. So that means it reproduces exactly, or not exact, it reproduces accuracy similar to the scalar code, although you enabled vectorization and permitted it to a great extent, I think. That's much more useful than just disabling or leaving it out, right? That is the purpose of that flag. Numerical reproducibility doesn't stop at the code generation level. There is, in the Intel compiler, you have very fine-grained control of math library. IMF means Intel math functions, which is usually meaning or referring to the scalar math library. You can define or request accuracy to as a whole, overall, across all functions. But you can also say, there is another flag, this is not mentioned on these slides. You can have a collection of functional domains down to single functions and request accuracy according to medium, high, and low for function domains. So you could say, for Intel compiler, you could say all transcendentals are allowed to be low accuracy, which just leaves all other functions at the regular accuracy, which is probably medium. Medium is, I think, the default. And then this is very helpful, right? If you know that your instruction is bottlenecked by exponential, but it is actually dealing with low accuracy because of an iterative approach, you can go for just relaxing exponential. This goes further for the vectorized part. You can request pseudo-intrinsics on the short vector math library. And then I don't know if you are able to request different accuracy. I'm not sure about it. But on the math kernel library side, you have SVML leveled up to multi-core, right? SVML is short vector math. It only targets the core, a single thread. It's not parallelized across cores. But on the math kernel library, you have some domain or something called VML, which is essentially SVML plus multi-core parallelization. And there you also have 3 buckets that you can request. And you can even do that programmatically. Let me just jump. Oh, sorry. Oh, yeah, maybe here. There's an example here. You can see it's a simplistic sample. It doesn't meant to work correctly, but it calls exponential function for a vector called in and produces an out result. And you request EP. Let's go back and see what EP is. EP is enhanced performance. It's the marketing name of low accuracy, right? That is basically the same thing. But luckily for marketing, low accuracy also means, oh no, low accuracy is separate. So enhanced performance is even lower than low accuracy. Okay, sorry. So you can think about what that means. I think only half the bits are correct as far as I remember on LA. Or no, enhanced performance, only half of the bits are correct. Anyhow, so for math kernel library, you have additional measures that spans multi-core reproducibility as well. You can cripple execution by also executing similarly on a heterogeneous set of systems, or CPUs, which is not really useful, I think. You could essentially have a system park of AVX2 and AVX capable systems, and you could cripple all the CPUs down to AVX, not AVX2, and then get reproducible results across the heterogeneous set of systems. But this is not very useful. The more useful thing is to get reproducible numerical results for the entire math library. Means all the algorithms that are in MKL can be enabled to be numerically reproducible in terms of the results. So they give you from run to run, that is the idea of, or the definition of numerical reproducibility, to give you the same result. When you start the executable, run it, gives you a result. You run it again, it gives you the same result. That is reproducibility. If you have dynamic load balancing or multi-core parallelization that is not numerically reproducible in general or doesn't claim it, you could have different results. You could think about a reduction that accumulates in different orders, a series of very small values into a bucket, an accumulator, and then a very large number which destroys it flushes immediately all the reasonable bits out of scope, and then you continue with small numbers, and you do it every time differently, so then it doesn't reproduce, right? So now we have this AVX 512 overview and flag, how to treat the compiler flags. Let's look at how to express vectorization. So there are different ways to use and express vectorization, and they differ also between languages like C, C++, and Fortran. Let's look at a picture. At the very low level, you could write assembler code. Means you sleep on top of the instruction set manual that Intel gives you as a download. I think it's thousands of pages. So you can, now it's not really required to write some small kernel. You can go with assembler code, but it's probably not what people want. Then you can do it at the functional level. You don't have to deal with register allocation. It's just normal C functions that you call, which we call intrinsic programming. And then you have some wrapper classes in C. They are a little bit aged, I think, on the Intel compiler side, and they may go only to cover 256-bit wide vectors so far, but they allow you to relieve you in a sense that they gave you overloaded operators in the past for utilizing the instruction set across different bit widths for basic built-in instructions like plus, minus, multiplication, and so forth. Actually, what they did, I think I remember that in the current compiler, they allow you to use that right away with the intrinsic types. If you write MM5012 and then you declare a variable of that type, you can now use plus, minus, multiplication right with these types. You don't need wrapper classes at all. The compiler enables you to write code as with normal scalar instructions. Then there is something on language extensions like OpenMP4 and some contribution. It's still called Intel Silk Plus, but you can find array sections, at least the most pleasant part of it you can find in GCC since several generations. I think 4.9 introduced array sections in C. And for very basic operations, you can grab, similar to Fortran, chunks of your array and then do basic operations and function calls with it. You can stuff it into scalar functions, and you get kind of a vehicle to vectorize explicitly. On top of it, you have auto-vectorization hints, pragma or directives, and even more on top, you rely entirely on magic like this auto-vectorization. I will walk you through 4 slides, as far as I remember, that give you an idea of intrinsic programming as it looks in the source code and what you include. This is not really something that enables you to write it, but it could trigger your interest, and you could think, oh, well, let me try to sync something in intrinsics and write some loop that the compiler may have vectorized for you manually on my own. You can do that. Basically, it's a little bit lengthy, this slide. You only need to include this header, and probably you don't even need to include that header, because the name is called, these guys are called intrinsics. What that is a built-in. It is intrinsic to the compiler, a function known to the compiler without any declaration, but for improved type safety, right? For improved type safety and checking at compile time, it is valuable to include this header, because then you get prototypes for all the intrinsic functions. And if you call this function with some operands, you get basic type checking, right? You know from Fortran and from C, probably you forgot about because you program just C++, but you can call a function with any number of arguments and with any type, and it never complains. It just complains at link time if that symbol name wasn't the right one. But you just proceed. And it is actually really a big hole in terms of type safety if you do so, right, on C and Fortran. So for that reason, you have prototypes. Data types look like this. These are, again, intrinsic types. They are built into the compiler. You have the guys for the different vector widths starting at 128, going over 256 to 512. And you have it as single precision, double precision. So you can see without postfix, it is normal, which means single precision. That's the normal thing for the compiler. Double precision is, double than normal. And then you have integer, which is also not normal, obviously for that guy. So you can keep in mind, you have these three flavors and the bit width for all of these guys. Then here are some intrinsics on, you have some pseudo-intrinsics that don't have hardware counterparts in the hardware. Eventually, they may have, but they usually don't. You can see exponential 2 function, which is not really in hardware instruction. Typically on KNL it is. You have add instructions and other things. Yes, so that's basically the way it works. And here's some example. You could imagine vectorizing to add A and B and write the result into C. And you would write a normal loop. And then it would consist of manual load instructions to load from A, to load from B, and to store into C. That's it, right? Here's the store instruction, and that is the add instruction, and this is the load. So it's very verbose. You can see what it costs you. Right? That is the idea of intrinsic, and it's to some extent reliable. So although there are many instruction set extensions, there are not so many that you need to do this change every week, right? If this is, I will give you that slide separately. Let's go one by one. This is actually a very interesting thing, because the application here in the browser is a guide. It's kind of interactive. You can type something into the search and find a reference for all the instructions, the throughput, the latency, and everything else for the different architectures. You can select subsets or categories or domains like cryptographic instructions or things related to bit twiddling or something like this. And the interesting thing is this application is written in Java, I think. This is the funny thing. So the intrinsic guide is written in Java. Anyhow, the question is then, why and when using intrinsics, right? The question is rather clearly to answer. You can think about if you have a clear hotspot in your application that is taking up most of your execution time, then it might be a good idea to write it down in intrinsics, because it's a one-time effort. You can tune it. And if you go out for a break, take some coffee, you return to the code that you haven't finished, you just continue with the same state that you had before, right? It is not that a compiler version changed, that auto-vectorization doesn't work anymore. You changed GCC, and luckily now it is able to vectorize, or it doesn't, or same for Intel compiler. So it is a kind of a dedicated, reliable vehicle, which is worth the effort in some cases. Let's start. SIMD intrinsic is just a single slide, just to summarize and give you an additional pointer. I don't want to talk about it. These are the little bit aged guys to wrap up intrinsics into kind of a C classes, and then give you overloaded operators on top of it. And I think this is much less, or it is much better to use the intrinsic data types directly. Some later feature in the Intel compiler and others, I think. And then there's something new, still not open source. I've asked again the guy from the Intel side if this is something that ended meanwhile up on the GitHub, but probably this is the intent. So if you want to help them to do it, you can rip it anyways out of the Intel compiler. It's a header-only library. It is called SDLT, SIMD Data Layout Templates, and it helps you to do our SOA conversions and deal with container types that are structure of arrays, array of structure, and it does it automatically. You write, instead of std vector, you use this particular namespace, and you have something else like array, and then you can even put structures into it, like a normal data type that have been declared as a plain old data structure. You probably know what I mean with POD, plain old data, and it turns it automatically into a structure of arrays out of this array of structures, right? And it helps you to vectorize, and it also does things like hybrid data type or hybrid container types. So it might use structure of arrays and arrays of structures at the same time, just to leverage vectorization the best. So it might be worth to learn from or to steal some code. I just wanted to say that. This part here is left over to Michael Clem. You will hear about how to do it in a standard way. How can I do it across different languages like C, C++, and Fortran in a kind of a unified way. They are dedicated or specialized towards the language. Like the Fortran way looks a little bit different, but more common to Fortran guys. But it is very something that you can rely on as a standard, which is neat. It is not any way into specific, right? And SIMDization or vectorization with OpenMP4 and beyond already works in GCC. So you have flags that you can apply at the GCC command line that enable the SIMD constructs and hopefully give you vectorized algorithms. One tiny word or summary on vectorization with language extensions. There was this Silk array notation, which is just a rethinking or push forward of something that Fortran always had towards C, and it ended up in C or GCC already. So you can use array notation, which is like array sections in Fortran. And you can see how that would work. You can turn this loop here into that. You see, you get rid of the loop, but instead of using indexes inside of it, you have placeholders that grab the whole thing, or left or right-hand side of the double column, you can write the offset and the number of items, right? It's not begin-end like in C++, like an iterator. This syntax means offset number of elements. In C++, you would usually write it as begin-end, right? But this is only a flavor. It's actually, in fact, similar to what, I think Fortran is closer to C++ in that case. Anyhow, so you can write that. Yes, exactly. Yeah. Well, I won't go that deep with introducing this. You can do a lot of things with the Silk array notation. I don't know about the status in GCC, and I don't encourage you to adopt it right away. I just wanted to point out, for Fortran side, it is very valuable to look at, despite of the semantic gaps and whatever issues. But for simple code, you can probably enjoy things like this that you had since 90s, right? But you probably still wrote another loop at this level, right? First of all, you have a dot product intrinsic. Oh, surprise, you don't need to write the do loop, because there is a guy which already does what you want. But it is even more complex. So you can see you rip out a vector out of this continuous or contiguous matrix representation. It takes the begin, this is actually C++ notion, begin, end, and multiplies it with the vector. You can see the shape of these two arrays that are involved into this dot product just declared on top of it. And you can see that the shape is conforming and that probably works. But this is basically something this is very simplistic, but you can use that in many Fortran codes where you have extensive, simple loops. And probably this is a much easier vehicle to vectorize, right? Exactly. So you can see the array section is the same syntax, double column here. Anyhow, just as a repeat from previous thing, you want to have the two components of the performance. Just to summarize also from the intrinsic section, you want to have optimization flags plus target flag. You want to permit vectorization if you stick with O2. And you might also want to use or enable OpenMP SIMD support in GNU GCC. There is a new keyword, not just -f OpenMP, but -f OpenMP -SIMD, which allows you to toggle SIMD and multi-core parallelization separately, right? You can disable and enable it separately on the command line. And if you write OpenMP SIMD constructs and have not enabled OpenMP, you could just enable the SIMDization separately if you wanted to do that. It's possible. But just wanted to mention there is preparation in GCC and proper support for OpenMP 4 and beyond. Let's go into the remaining part. I think, yes. So this is only a placeholder. It's a dummy line. This is, again, Michael Clem. And some interest, the only thing that I wanted to highlight here is OpenMP SIMD, since we heard about it, is not just about hinting loop vectorization. It is also about a new construct. It's not just to cover the legacy and what you had before in a standard fashion. It also gives you new constructs like SIMD functions. You can now write kernel functions. You can write a function that not only takes scalars, but a section of array or an entire array, and which is a scalar by itself. So it looks like, to speak simply, it looks like OpenCL or CUDA. You write a function which is a kernel function. And that was something that any OpenMP compiler or vectorizing compiler, to speak better, had to do anyways, right? If they had auto-vectorization for a particular loop, they always generated a kernel function out of the loop, right? But now you can express that yourself. So it's a neat vehicle that you might have a look at. And for some applications, this is not only an optimization vehicle, it is also something that sometimes expresses right away and in an easy fashion what you actually want. You can write scalar code, but you get it vectorized or scalarized by the compiler. Anyhow, I have a last gourmet topic for this first compiler part. It's called multi-target functions. I think this is actually what GCC understands underneath of it. It is a feature that Intel compiler always had, and it was in the past we talked about normally not in this audience about this, because it seemed to be not interesting for scientific and open source application to have anything about multiple code paths, which just adds brittleness, right? You had a binary executable, which not only contained AVX, but also AVX2, and surprised something more. And also use CPU ID dispatch to decide which path to go. But this is also useful for open source application, I think. And let me just jump ahead. Why? I will see if this is on the next slide. No, I think it's here. The reason here is basically it can simplify and control the build step of an application. If you build a library which is general use, right, and you cannot know which application adopts your work, and you've, for example, used intrinsics within that library and say it is a C++ library, header only, you can now write multi-target functions that are then taken according to CPU ID, even in an unknown application environment. Some compilation environment which doesn't apply target flags still gets optimized functions according to the best code path according to CPU ID. I think this is worth to look at least as a library writer to look at this. Anyhow, so for GCC, you can enable functions with intrinsics by applying the architecture flag at the command line of the compiler. But you can also use attributes, target attributes. It's underscore, I probably have an example here. You can see this. This is the GNU way. The Microsoft Windows world has a decal spec very similar, but you have this attribute. Then there is a new keyword since some versions that's called target, then a string in quotes and double quotes. And it takes a comma-separated list of instruction set extensions that you want to target. And that permits you to write intrinsic code for a function that is decorated with this target flag. And that also works if you just include a header that had such a function into an unknown environment where no target flag at all is applied. Right? And you still get something. And this is basically the flow on how to do that with an open source application. You would decorate some functions. You would give them a postfix for the different code paths that you implemented in intrinsics. Say you started with AVX, and you also, for fun, made FMA, and on top of it, call it AVX2, and maybe soon KNL, whatever. And then you have a normal function without postfix, call myfunc, and it would decide which one to take, this guy or this guy, right? And you take a CPU ID utility, you can grab it from there, just as an example. It's floating around multiple hundreds of times in the web. You can grab the code, whatever code you want. And then this wrapper function essentially decides to go that path or that path based on the CPU ID. That is the way it works. And you can optimize it a little bit further if you have fun about these kind of things. You could avoid, this is obviously a function pointer call rather than an inlined code, right? You always had to deal with function calls because of that. But if the static code path is sufficient, according to the best code path that you implemented, you can get rid of the function call as well if you like to do so. Yep.
So I have a question.
Sorry.
Thanks. The mechanism with the CPU ID is basically for example, I make a call to a library, and the CPU ID resolution happens at the time of the call and then gives me the correct
Not really.
pointer?
No, it's not really. It's also, I just jumped over that in this flow here. Actually, in the second step, you would set up a table of function pointers in advance. There is no need to decide this every time you call, right? There is no need for that kind of control flow. You would just set up a table or with a single pointer, function pointer, they have all the same signature. The only difference is if it is AVX internally or the containment is AVX or the content or AVX2 or whatever. And then you set up the pointer as part of the program initialization, however you do that. Whether it's C++, then you can write down a structure or a class in any translation unit and it gets automatically initialized. Initialization order between different translation units is different, you know that, but it is automatically set up prior to entering the main function, so everything is ready. On C, it doesn't work like this. You have to call an init function or do some attribute that calls it automatically. There is some specific, there's an attribute CTOR.
Yes.
Something like this, but you can also, if you know that code ends up in a shared library, you also have hooks that are called automatically when the shared library is loaded. It's your turn. You can do whatever you want. So, yeah. On the Intel compiler side, sorry.
I also have a question.
Yep.
What would be the impact of the size of the binary when compiler does multi-targeting?
Yes, so compiler's multi-targeting is based on heuristics. So if the loop boundary is known, of course, it knows if vectorization is ever possible. If you do 100 loop iterations, it probably doesn't generate an additional code path for it because it just gives you more size, no advantage. The remainder and the peel is more overhead than you ever get from that. And if the loop boundaries are completely unpredictable or hinted to be large, you also have pragmas and directives to hint the loop boundaries, which is actually very efficient. It is better than saying unroll. And then you can essentially, the compiler heuristic, that's the case in Intel compiler, is essentially deciding for you if it generates a multi-version function. That is the case. This is what I said. This gives you brittleness. Because you might only see in a profiler that you ever entered AVX2 or that you never entered AVX2. You might ask you, oh, why don't I get the right performance? I used multi-target functions but enabled AVX, but you never got AVX. If you look into the profiler, you never executed it. No FMA, because the heuristic just denied to give that. There is a global flag on a per translation unit basis, or of course on the whole program. You can say aggressive multi-versioning on the Intel compiler. You can tell them, hey, rethink about your internal heuristic, do more. I don't care about the binary size, just do everything in terms of, it's possible as well. Okay, so then I step one further. On the Intel compiler side, I won't spend too much time on that. The dispatch has been there for a long time, and you can do CPU ID dispatch on a function level in a much easier way. I don't know if that works for GCC. I don't think so, but you have some pragmas or some attributes that you put in front of the function, and you get basically an overload, or it under the hood generates multiple versions. And you don't even have to deal with CPU ID. The compiler does that for you. It does the table, it initializes the table, and it calls it into the right function, and you don't need the wrapper function at all. So this is all done by the compiler. And this is the same. This is just the Windows notion. Instead of decal spec, you can also write attribute. And then you have CPU underscore dispatch. And then you have some weird Intel compiler collection names for the code path that you want. I have a table about the names. And this is a kind of decorating that function. And it is like, even for C code, it's like overloading that function. So it's the same mechanism I've shown on the previous slide. So it's much easier. So these are the names. But basically, what I covered in this chapter, to summarize, is a manual mechanism to get the same functionality that I just wrapped up with on the Intel compiler side. So you can do the same manually on your own, but I think it's worse in some cases. Any questions on that? Otherwise, we would have a break, questions anyways, or step into the next, or the last remaining part.
Okay, I have a question.
Okay.
So, what is the performance difference between align and underline store and load intrinsics?
Okay. So, let me put this this way. You have pragmas and directives to hint the compiler to generate aligned stores or aligned loads. And if you ever looked at the assembly generated on, say, classic Xeon, it always generated unaligned load store instructions, probably the source of your question. It never generated aligned store or load instructions. The reason is, on this architecture, if the actual memory address is aligned and you use an unaligned load store, it gives you the same performance as if you had used the aligned or the aligned store and the aligned load. There is no additional performance advantage. And that is actually the reason that they decided to go for safety. Because if you, for some accident, gets an unaligned address into that program, it crashes right away because of unaligned load store instructions. It might be still useful to force aligned load store on KNL because of these splits, right? But it's actually not true. If it is aligned, cache line aligned, it is cache line aligned, right? You peel the loop until it's cache line aligned, that's it. It should work. More questions? Okay. So what I left out actually is there's much more content on telling the compiler that this is an aligned guy or not. There are pragmas to hint a loop to deal with only aligned data, which in the worst case or in the best case, depends on the view, just leaves out the multi-version, right? That is actually some benefit. If you tell in front of the loop, this is aligned, the only advantage that you get on the Intel compiler for classic Xeon architecture is that it doesn't generate a multi-version, which deals with unaligned versus unaligned data, with aligned versus unaligned. It just gives you a little bit less of code. That's not a big deal, I think. Sure.
About the multi-version, so if you have MPI, two nodes, one with SSC and one with AVX, and the multi-version, so it will understand and execute?
Yeah, so the multi-version is, the decision is made based on the CPU ID, on the actual CPU that sits in that node. If this is the same CPU, the code path will be the same on both CPUs.
So it can be helpful in that case.
Yeah.
More questions?
Okay, I think there's no problem with no questions, because we have the remainder of, or actually the second part of the compiler session, unless we take the break right now, or some break, there is actually more interactive, because it is only a collection of examples and probably just 15 slides, not much. So it's not another hour of things. No, it's yeah, if we want to have a break, otherwise I can just wrap up in another 15 to 20 minutes and we see some examples. Maybe that's inspiring. Yeah. I think it's the same title slide. It's no difference between, but the content is different. It's an example collection. I'm not completely naming all the examples, and I don't know if they are all useful by itself. I recommend you to attend tomorrow's application sessions, where we have actual use cases connected to an application that does something useful, right? This is only a loop or a code snippet, and it might not apply to you at all. Anyhow, for tomorrow we have more to learn from actual examples along with actual performance results. So we will see comparison with other Intel hardware. I also have occasionally some comparison to some GPU implementations. So tomorrow might be more entertaining from an actual application side of life. But here we have just artificial examples. So there is some sequential reduction. This is a C thing. It's a C++. It's not. So Fortran, I think all Fortran programmers are just relieved from that problem that I will just point out here. The problem, can somebody see the problem of this kind of code sequence written here? So is there something wrong? This is not correctness. This is fully correct code. It compiles, it's fine. Or if it doesn't compile, it's a typo in the slides. It's nothing. I will help you. This is always a showstopper that if such a question stays for a long time in the room, you can see this is something where the C compiler is surprisingly, what you see is what you get. You can see that this guy, the loop induction variable I, is just varying with the outer loop, but not with the inner loop. But it produces you the performance as if that is a J loop, right? It does an actual store instruction every time for every J iteration. Unnecessarily, right? The compiler doesn't pull that out of the loop and omits you from writing that to memory. It writes to memory every time, and this sequential reduction example is probably, there might be an 03 flag that makes that unhappily or happily working, but in general, overall, is the problem is that you want to hoist out that variable as a local variable or global, whatever your flavor is, accumulate into it, and then do the write only once. That gives you immediately 10-fold, 100-fold, whatever the loop iteration here is in performance, just for hoisting that out of the loop. What you can learn from that is the C++ compiler, to some extent, is unexpectedly literal. So it gives you what you wrote. It's like a Microsoft Word. It's what you see is what you get. You wrote store and you get store. There's some comment.
May I comment on that?
Yes.
That's not a problem with the C compiler, it's the C++ compiler. That's actually a problem of the broken C++ syntax.
That's true. That's the bonus. It's actually in the fine print here. The side effect may speak against compiler optimization to just do that for you, right? There is no reason that a compiler would not hoist that for you rather than letting you write that code on your own. But the reason could be they had to assume that this is running thread parallel, and writing to that memory destination needs to happen. You want that, right? Here you only do one write, and maybe that same procedure runs in parallel on a different core, and it writes into the same memory, the same array, right? And if you do the write every time, this is obviously more accurate or more current. It's all dirty reads, right? It's dirty reads. It's bad. Probably you don't want to have this code working that way, but it is definitely a side effect, and the compiler respects that this side effect exists and then gives you what you requested. That is simple, the bonus on top of it, yeah. There are other showstoppers. They are taken from actual applications, but they are anonymized, right? They are not specific to this application. So you can see code like this here wouldn't vectorize. Neither if, say, this function is inlineable, then it would be vectorizable. But think about this function is actually a system call, a printf, or an IO operation, something that you never are able to vectorize because the compiler cannot inline that kind of code. It comes from a standard library. It's an operating system call. It cannot be inlined. Then this would never vectorize, although it is very nice. It is the inner loop. The outer loop is parallelized, so it's the ideal world. Outer loop parallelized, inner loop vectorized. But it wouldn't vectorize because of that. Unless you strip it. It's an assertion. The reason here is basically this parallelized, and that is not vectorized, as I said, just because of this is not an inlineable function. That is something you should keep in mind. This is the biggest source in actual scientific applications, that you have very big loops that are fed in terms of content. Sometimes, if you look at the code here, you cannot even see the outer loop. It's way up somewhere. It is in the outer space. You can't see it. You work here, and the colleague that already died 10 years ago, he wrote the outer loop at some point. That is maybe the real case. And then you just sit here and pray that all functions along that path for the whole nested loop are all inlineable. That is basically what you want from this vectorization thing to happen. And it doesn't help you if you have OpenMP4 and SIMD functions, because 10 years ago you didn't have SIMD functions, and so you just sit here and pray that this vectorizes. That is the basic thing. Or you do black magic like LTO, like link time optimization, or on the Intel side it's called IPO. It's not selling the shares of your little company, but it is a interprocedural optimization also across different translation units. Then the compiler actually collects everything, and then you have the binary blob at the end, and then it goes over the code again, and then thinks, oh, now I'm seeing this kind of function code inlined here, or I could inline and then vectorize, and then it adds a great extent to the compilation time. IPO or LTO is rather slow typically, or memory consumption is high. There is a question.
So how many inline function can I put before it does not vectorize anymore? Or there is a limitation?
There is a heuristic. If the function is seen in terms of the body of the function would eventually be not inlined or marked as a candidate if it contains a loop. I think that was a very simplistic heuristic that compilers used in the past. Maybe it is more sophisticated. Because if the function contains a loop, it is in the first stage eventually not marked as an inlineable function because it is fat enough. That is basically the idea behind it. Therefore, it is worse to do the call. But if it is called inside of another loop, it would have been valuable to inline the whole thing and then vectorize it across. You never know if this is a good heuristic, but that is one. I don't know about others. Probably there are more heuristics that you can pull in. Anyhow, so this is good. I think there is more on this collapse. I think it's not really a necessary keyword. I just wanted to remind you that it exists in OpenMP 3.0, which nicely settled across GCC. LLVM is a little bit a deviation, but Intel compiler and things like this, you have collapse keyword already. You can collapse perfectly nested loops, which is not really extremely useful because perfect is the bottleneck here, the problem. Perfect means there is nothing between this kind of sandwich here. There is nothing else you do. Perfect means you could have multiplied the loop ranges yourself, but the compiler is nice enough to do it for you. So these two loops are collapsed by multiplying these loop ranges together, making an artificial single loop and to peel the I and the K index separately using the mod function for the inner loop. In front of the inner loop, there is some helper code that resurrects I and K out of an artificial index, which consists of these multiplied ranges, right? The upper bound for this single new loop would be n square, right? That is basically the way it works, and then you would have some stride and things like this. Anyhow. Okay, so we couldn't learn much about this, but you can do something else with it. You could actually trade parallelization between multi-core parallelization and vectorization if you wanted. I don't know if this is really inspiring, but you could extract some loops out of this inner loop and push it into the outer loop or make that loop range larger, right? The reason is if this is a small value, A is 4, but you have 64 cores, not 4, right? This is not useful to be parallelized. It would just use 4 cores instead of 64. But if you could somehow make this loop range larger, you can at least use more cores, perhaps. And that is possible by extracting some loop iterations from the inner loop and put it into an artificial mid-size loop if you want to do so. And then you can collapse these guys together. Although this guy is strided, the compiler should be smart enough to collapse that whole thing and do something for you. You get a little bit more heavier, say, integer operations to calculate the indexes, but you can pray that this is better than having a single core application in this case. There is more you can do for scientific applications. This is a real-world sample. This is not anonymized, but it doesn't care. You don't have to care about it because it's from Cineca. It was a workshop we did at Cineca in Bologna. We did something with Yambo, which is kind of an on-top, add-on, or whatever you call it, on top of Quantum Espresso. And it calculates something else, right? But anyhow, and it's also, you can see it's a while ago. It's 1 year, 1.5 or 2 years ago. But anyhow, there was something that didn't scale in one of the main loops. And it was because there was some OMP critical just in the middle of a big loop. And it was actually accumulating some vector multiplications, or it modified a vector of a very big and large distributed matrix. And it updated matrix columns inside of the loop. And in order to do the update for the matrix columns, it used an OMP critical. First thing you can criticize here is you should have named the critical, right? If you omit the name, it refers to the one and only global single named critical log or log, and which is shared across your entire application, right? First, you want to add a name for the critical. Call it my log, my stupid code, which is whatever it does. And then, okay, it doesn't help you with performance, but you sleep a little bit better because you got that right. And then you want to turn it, unfortunately, you have to use OpenMP API instead of just sticking to the directives. But what you do is essentially, here you set up a fixed size array, say 16 entries, 32 entries, something like this. It just contains OMP mutexes. Fixed size, it's very easy, 16, power of 2. And then what you do is this loop here is, say, the induction variable is I. And what you then do is you use mod operator and you say mod 16. And then you get, out of all I indexes, you get always a number between 0 and 15. And this is used to address one of the locks that you just set up in front of it, right? This is here. Set up small fixed array, 16 locks, and you take any of these, 16 locks. And instead of locking or using a single lock, you use 16 locks. So at this point in time, you permit 16 threads to operate in parallel on all of the matrix columns that are not the same column, right? This is a very simple thing, but it's not too obvious. But, sorry. it gave an immediate better scalability. You can see no scalability versus some scalability. It was flattening out, of course. We had, I think we adopted 8 or 16. You can see it flattens out. Also depends on the matrix. If the matrix is less than 16 rows in that MPI rank or columns or whatever we talk about, of course, if you use 200 locks, it doesn't help you anymore, right? You have just 16 rows and no better parallelism, but much better than using a global critical at that point. Anyhow, let me wrap up with this and look at other synchronization primitives that are not used so much. It's by no means sophisticated in any way. It is just, just a reminder. I've seen code looking into atomics, which is okay. Atomics are okay. Atomics, if the operation that you do, like plus or minus, is primitive enough to have a prefixed instruction on x86 Intel to make that atomic, you are done. It's okay. But usually floating point operations and atomics doesn't look too good. And also scalability of atomics across multiple sockets is obviously not a good idea, because you have to communicate to your neighboring socket, and probably the compiler or whatever the entry point into the atomic operation is, it needs to set up something else that is, or the architecture enters a very weird slow path to make the atomic correct. Anyhow, so there's also some shadowed, you can also use thread local storage sometimes. You can do thread private array in Fortran just to give you some variety. Of course, you can do a global big array. You don't need fancy thread private. But you can do also a global array and chop it up yourself, like MPI does. You just have an index, and then you calculate which part of the array is your part for your thread, and things like this. But it definitely allows you to do more sophisticated things than immediately saying OMP critical, right? And it gives you better scalability in many cases. This is the very last thing that the compiler does. It is a little bit of magic, but it is a preparation of which flags you might use or which pragmas or directives you want to look at. At least from my perspective, some of them are useful, some of them are not so useful. And this is just a preparation. If you have this loop, oh, sorry, I forgot the source code. This is ideal. We just see the vectorization report instead of the original source code, but this doesn't matter. It shouldn't distract us. But you have optimization reports for all phases of the compilation in Intel compiler, and you can do high-level optimizations, which are about, we interchanged the loop, we split the loop. So why would you split a loop? You would split a loop if you have register pressure. If the content of the loop, the body, contains too much code, which involves too many operands, you eventually want to split up the code into 2 separate loops. And then you get the first guy operating with the entire register set, and the second guy does that on their own without the register pressure in between. And there's actually even in Pragma to make the loop split for you. You can still write the big sandwich loop and split it artificially using just a Pragma. You just write in the middle of it Pragma distribution point, and the compilers on the Intel compiler splits the loop into 2 as if this whole thing would be 2 loops. It doesn't sound too useful, but if you have a deeply nested structure where, as I said earlier, the outer loop is 10 years ago somewhere on the outside in the outer world, it is nice to do it this way eventually. Anyway, here is something that the compiler might do in terms of loop transformations. You have the left-hand guy, and then the compiler turns it in the right hand. Right? It splits the operation, the sandwich here, into 2 separate loops, or actually does something else. And you can get a report and read the optimization, the high-level optimization report for that, what the compiler did. And sometimes, I'm just saying that you can even learn from that. So you could say, okay, the Intel compiler did this, and it looks like as if that is beneficial. And if it doesn't destroy all the source code that you had before, it might be a good idea to just write it that way, because then you get the same performance or similar performance on other compilers as well, just leveraging some of the rewrite capabilities. Anyhow, what I really wanted to say is you have a lot of pragmas. This is just the C++ reference documentation for the compiler. But this is similar for Fortran. Meanwhile, on Google, you can find the reference documentation for any of these compilers. It was a big problem for Intel in the past, but you can do it meanwhile, and you can get a documentation, or actually, this gives you a landing page with a list of all Intel-specific pragmas. And they also included a landing page with all non-Intel-specific pragmas that are present, say, in GCC. So it's very useful to read this and to adopt some of them eventually. For instance, you don't need to unroll simple loops. You can just use a pragma, which is present everywhere. And then, let me wrap up. There is a question now. There are projects that don't allow or don't want any directives in the source code, which is okay. I mean, to some extent, you could end up with so many code, a handful of code, but on top of it, there is a bunch of directives, tens or not more, but really a lot of directives that hint and massage the code, how it should go. This is not really something you really want to have in your application code. But you could essentially wrap up vendor-specific pragmas. By definition, pragmas are always specific to the compiler. This is the whole idea. If it sees something that it doesn't know, it doesn't complain about it. The warnings in recent compilers actually doesn't look like this. They tell you, oh, there is an unknown pragma I don't know about, which is a little bit odd and annoying, because you want to have the whole thing quiet. The definition of a directive or pragma is be quiet if you don't know what I mean, otherwise do. And you can wrap that up for C at least, for C and C++, which might be interesting if you are a library developer. You could come up with a header, macro header, which uses C99, there is an underscore capital pragma, or a compiler-specific underscore small pragma, which then allows you to take the name of a pragma inside of as an argument, as a double quote argument. Sounds weird, but this vehicle can be repackaged as a macro again. And that is very good, because then you can introduce something like pragma unroll, right? And now this pragma unroll, if it is Intel compiler, it's called pragma unroll. If it is GCC, it's called pragma unroll. Okay, it wasn't a useful example, sorry. But there are others. There are things like alignment, I don't know. You can look into this kind of guy here. You can find a lot of pragmas that are different named or slightly different under different compilers, but actually are useful to be used or wrapped up. So you can wrap up pragmas and have an abstraction level, which is independent of the Intel compiler and more portable. And probably it's helpful. You write it only once, right? You make one helper header, and then you're done. Actually, this is a good keyword. This is not really useful anymore because we are almost done entering discussion, but there are other flags for the Intel compiler that I've found useful in the past. There are tons of flags, hundreds, I don't know. We probably forgot what they mean, and you can look it up what they mean, but something dealing with complex number arithmetic and limiting the range and the overflow behavior of these operations is sometimes at KNC time frame it was beneficial. Fast transcendentals are beneficial to be tuned at some point. If you have code which does exponential functions and you don't want to go intrinsics or something like this, you could do something like this and happily get eventually big speed up. And you can also tune it further. There are more weird flags, just to give you some variety. IMF domain exclusion, it tells the thing, oh, it always stays as a normalized floating point number. It never gets some border case, right? Because the problem with these arithmetics is if an exponential, remember exponential function, if you stuff more than 707 or something like this as an operand into the exponential function, it is already out of range in terms of a double precision number. Remember that. And if you do that, if say a good percentage of your array content is larger than 700 and you call it with exponential function for every guy, for all of these larger numbers, you enter very slow code paths on the Intel architecture and probably everywhere else, because it needs to handle the denormalized or the degenerated case in a very specific fashion. It's very slow. So you don't want this, and some of these flags here deal with that. You just tell them there is nothing like this, and if I don't care, give me an infinite for it, for a number that is larger than 800 to exponentiate it. There was something on pre-15 compiler, as far as I remember. The GCC GNU compiler collection by default assumed anti-aliasing rules for the entire C application, which wasn't the case for Intel compiler. It had better vectorization capabilities for sure, but it didn't vectorize in some cases where GCC vectorized. If you still have old installation of that, of Intel compiler like pre-15 or 15, I cannot remember, you have to look it up, you probably want to use ANSI alias. But if you are a mistrusting person like me, I always, sometimes flags depend on the order they apply, and the last word counts, right? This should count, but in the very past, I think there were broken compilers where you wanted to remove all aliasing rules first, lying, saying, oh, no aliasing. And then you wanted to add aliasing on top of it, but only according to ANSI rules, something like this. This helped quite a bit with older compilers. And with also since 5 years, there is something on IFORT specifically, because you deal often with, with fixed shapes and, stuck sized or not so, you have known shapes for arrays. And you can tell the compiler to just align those for you, where the compiler previously did some implicit memory allocation. You tell them, oh, and by the way, please all align these array allocations for me, because 64 bytes is luckily just 512 bits. So it gives you an alignment that suits the 512 bits a bit better than, say, something else. I think that's it from my side, and I'm happy to do or answer more questions and answers, or answer more questions.
Okay, so I have a question. I will start. I remember when I was looking at the report from the Intel compiler, there was always this generated memcopy, generated memset. Yes. So what are those functions better than like memset, for instance, like just a vectorization of loop? What does it make the difference? Because I guess there is a function call made, but there's a cost.
It's true. Yeah. So the thing is, there is a pattern recognition for zeroing a buffer. Pattern recognition for doing something similar, something else like memset would do for you. And they have specific intrinsics, basically, that they pull in implicitly as soon as they see something like zeroing an array. And then they pull in optimal CPU ID dispatched code based on that. And it sometimes worked, it sometimes didn't work. We had this complaint about memset on AVX and particularly on KNL ourselves, I think. Many application engineers complained, oh, memset comes up in the top ranks of our application. What happened? And I think this is flushed out with newer compilers. There is this settled, but I give you something on top of it. I probably forgot this actually in the previous slide deck. Let me switch back. Yep. Because sometimes, no, I have some. Okay, yes, so there is something here. that I omitted last time, which is related to some extent. This is actually an invitation to join 2018 compiler or Intel compiler, the next version. You can enter that thing or click it, whatever. It is for April 19th, it's a demonstration of what new features they added to the compiler. It might be not too interesting, but I made this slide and gave you an overview what actually comes up to some extent. But there is for SVML, for small vector math library, there is something like static dispatch, which is really related to your question. So we also saw issues with math library functions dispatched according to CPU ID unnecessarily. The guys just they generated only one code path for AVX 512 mic, whatever. But they still got a lot of CPU ID dispatches for small vector math library functions for no reason, right? They had overhead because of this CPU ID dispatch. It's an indirect function call. You have to take the call, and it's an indirect lookup also. And now the rules changed for that. And I think this is very similar to memcopy and memset functionality, which also boils down to certain intrinsics. Also, the same is true for string functions, like processing, scanning strings, how to do that. There is a variety on things you do with Intel instructions. And the -X now gives you statically dispatched SVML functions, no CPU ID dispatch. Of course, with -X, you have CPU ID check in front of main, but this is no problem. You get rid of the entire thing during the execution. But yeah. Actually, there is something else. If we would talk forever, but I will just send this by email. You will get it. For those C++ affine people, we have something, an Intel implementation of parallel STL. Sounds like, oh, I see some of you wake up. There is some proposal for C++ 2017 and beyond that increasingly adds parallel algorithms to the STL. And there will be an Intel-specific implementation, which is different. It doesn't add an Intel-specific standard library, but for the STL part, there will be an Intel-specific version which is parallelized and vectorized. And underneath, I have a separate presentation. You can just look at offline at this. It will use TBB underneath, which is probably a very good idea because it is deployed since a decade and longer, and is very performance stable and probably a good idea. It's also composable. If you have nested parallel algorithms, it probably works out of the box much better than rewriting such code from scratch, right? There is something good already, and yeah, so might be of interest.
Any other question? Okay, well, we can thank Hans for this very nice
scientific applications in general. On the other hand, or that also means that the compiler or our compiler and others as well are essentially asked to generate such code regularly based on high-level code. So the goal with a general instruction set extension is to generate that kind of code out of high-level languages like Fortran, C, or C++. It is not the intent to rely on an intrinsic enabling. In contrast to that, domain-specific ISA extensions are often not meant to be covered by any high-level code generation. So there are also examples from the Intel side. You can see they're listed like CRC32 instruction in SSE. Probably there is no idiom recognition in Intel compiler to capture some bit twiddling, which would be better written as a CRC32 instruction. No, you had to always write it explicitly, right? Or use a library that did this for you. And same goes for other cryptographic extensions and maybe other domain-specific extensions. So there are these two kinds of meanings behind instruction set extensions. With AVX 512, as I said, it's not only a promotion from 256 bits to 512, it is actually a rethinking of the instruction set architecture that Intel had, despite of keeping the naming like AVX. It gives you more resources, as we heard earlier from Michael Clem. It gives you 32 registers and wider registers. So it's a big resource increasement, basically. And it also gives you an entirely new architecture on the masking side. So previous architectures, or AVX, for instance, they used regular registers to keep masks around, right? If you wanted to leave out some of the entities in a vector or in a vector, you used another vector, like an integer vector, to have zeros and ones collected into, but that wasted a lot of space. As you can imagine, for every state, which could be 1 and 0, you just wasted an entire 32-bit integer or something else, right? And there is no need for that. And as the vectors become longer, that becomes more of a problem. So the instruction set actually also introduced additional registers, K registers, to cover masks and things like this. And also unified the instruction set in the sense that all instructions can be masked. It's not just that you have few of them enabled for masking because someone anticipated that that might be useful. The entire variety of all the AVX 512 instructions allows you to use masking. And it is also unified in the sense, you might have heard in the past, how many operands an instruction has. That is also answered by AVX to some extent, AVX 512. It is always the 3 operands per instruction, right? You heard about FMA 3 versus FMA 4. And in any case, just to make you aware, I have 2 parts about the compiler, but I don't want to make it very invasive or brain filling. So the second part is much lighter and shorter, so we will have more time for questions and things like this. Also, in case I'm overspilling out of the first part, I would just continue the rest of it into the second. So we have this time a little bit of relaxation. If you remember the agenda, we will have 2 parts on the compiler, and we will have some time left for at least for questions and a bigger discussion, I think. This content is not run so far. This is not the usual compiler presentation that we have at Intel. Probably you can imagine we have a lot of engineers who like to present you a lot of details. So the standard deck, to make it short, is more than 200 slides just on compiler, vectorization, flex, and examples. So it's probably we die after such a session. So for that reason, I try to collect something that is more meaningful for your case. And the second part is actually entirely a collection of do's and don'ts. No, not really, but more practical things. So you can see the intro or agenda for this talk for the first part. It gives you again some intro on the Intel AVX 512 instruction set extension, but it will also give you the status of the compilers. I said compilers, not just Intel compiler. This includes explicitly the GCC, the GNU compiler collection, as well as the LLVM Clang compiler, and which version you should expect to be okay for AVX 512, and what you can expect in terms of auto-vectorization capabilities, perhaps a little bit about. Then some newer features also on how to actually deal with vectorization in scientific codes. Sometimes you see a lot of codes that just leave out any particular target flex or generating AVX or AVX2 or whatnot. They just rise the optimization level and that's it. And we will see how to deal with, say, regression test failures or reproducibility issues, and how to get vectorization plus reproducible accuracy and some reasonable trust into the vectorization capabilities. Then we will look into the expressing vectorization, and I will leave out a very pleasant part, actually covered by a public and available standard like the OpenMP 4.0. I will leave this to my colleague, to Michael Clem, but we'll look into a little bit of an overview of intrinsic programming. I know it's a stretch goal because some of you already do work and go deep into it. Others never heard and probably don't want to touch. But it might be interesting for you at least to look at what is that kind of thing. Everyone talks, or we talk often with all AVX 512, it's 3 operands, and in most cases, for almost all instructions, that means you have non-destructive behavior. Just as an explanation, you load the source operands, and you produce a result, an output. And it is fully sufficient to rely on 3 sources, essentially. And only some instructions are exceptional that might require more inputs or outputs, which is the case eventually for FMA, which is one exception, because it is also an exception in itself. It is basically 2 instructions in one instruction. It's a multiply and an add fused together, so there is nothing you have to wonder about that this is requiring more than 3 operands. On the other hand, it also means FMA3 is destructive, to just give you some deep dive on that side. Let's look into more and larger registers. You can see this is a natural extension, at least from the naming. You have this Y register set for the 256 wide instructions, and you have the Z registers that just double the width of the registers, and then also give you more general purpose. It's exactly 32 of these 512 registers. And then you have essentially 16 elements per 512-bit vector in single precision, or 8 double precision elements per vector that you can process in one instruction, basically. And it also gives you an idea, why do we want to have instruction set extensions or vector instructions at all? Because you do one instruction rather than 16 or 8. So you have something that we call instruction size reductions. Not that the size of the instruction becomes smaller, that could be also the case, but it also means you have fewer instructions, right? And if you run at the same clock frequency of a processor, and you run you essentially run fewer instructions, there is a potential that you get more work done, right? Because that is the case, the simple motivation for all the vector instructions. And as I said, you have 8 mask registers, K registers, and I think I will give you something more on the compiler status with respect to GCC. I believe, for the top of the head, 4.9 version of GCC introduced the very basic enabling for AVX 512, and 5.2 filled in the gaps. In particular, just to give you this at this point here, I think in the very first shot, the 4.9, the maintainers rejected K-register implementation. So none of the intrinsics that are supported in 4.9 allow you to be masked, because the infrastructure in GCC isn't or wasn't there at this point, but this is filled in. So you've been about it, and what is this about, and how much can you gain from it? And then we will also look into array sections, and some of the topics are not necessarily new, right? Some of them are pretty old if you think about Fortran 90 and array sections, but they are still not used, although they are a good vehicle to do explicit vectorization to some extent at least. And for the OpenMP part, as I said, I just wanted to mention and forward essentially to Michael Clem's talk, which is, and I just forward you the most interesting parts or mention them. This is the loop vectorization and the kernel-based, the SIMD function-based vectorization with OpenMP 4.0. And in the end, I have a little bit of a special topic, like not a gourmet topic, but the small kind of thing on how to get going with intrinsics when you rely on GCC or LLVM, because there is some caveat with dealing practically with these intrinsics. I think I will relieve you from history of instruction set extensions at Intel prior to 2009, but you can see there is a long line of things. I will come back to that, why that is, but let's look at the more recent things, like this is pretty outdated, the slide, you can to be done, but we can fill in the number, I guess. For KNL and for Skylake Server, you can see the AVX 512 materialized, and it is not just promotion of vector width or instructions to 512-bit. It is really a kind of a new instruction set, which breaks to some extent with previous AVX. So it's not only a natural extension. We will see what it gives us. First, the motivation here is, why do we want to have, or why do we get all the time new instruction set extensions? The truth here is probably, to some extent, that hardware innovation happens to a large extent at the ISA level. This is true, I just wrote that down in the smaller print there. This is true for CPU as well as GPUs. You've seen that recently for machine learning. There, the whole domain is now covered by new instructions like half floats and lower precision instructions. And it means the innovation to get better performance for a specific domain wasn't because of something magic. It is actually happening at the instruction level architecture, which is true for CPUs and GPUs. So that is probably something normal, right? If we discover in our hardware-software co-design some gap with an important application, we explore immediately, or we explore the possibility to fill in that gap on the instruction level. And just for terminology, domain-specific versus general, AVX 512 would be some general instruction set extension that allows you to express basically anything you want, not just a specific, say, cryptographic algorithm or accelerating this or that, but it is something that allows you to write with regular GCC 5.2 and beyond. You can just work with masks as you like. And there are 4 different granularities that you can get. You can see this, you have different mask granularities, but I think this is a detail you can look up yourself. And the motivation is already given with the mask registers. It's basically, it would be a huge hock in the size if you used general purpose registers instead of real bits or only bits for masking things out of a vector, because you can get it in the left upper or lower corner of the previous slide. I will jump back. You've seen you have 16 elements of single precision in such a vector, and now that allows you to just use 32 bits to mask any of the states that you want, right? Rather than wasting a huge register for that. So masking would be useful in general. Right? You can use it for very simplistic control flow things, like deciding about only one thing. Of course, if you decide about 2 things, you can repeat the control flow and just think about making it a masked version again. But in general, you can turn simple control flow into a masked execution if you like. In many cases, this is possible. But it is also useful for remainder handling or loop peeling. Of course, maybe loop peeling is not a good idea. You need to peel until you have a multiple of the vector width and until you are aligned in memory. Then you may run the main part of the loop, which is basically some job that your compiler does for you. And then you eventually have a remainder, and then you have different choices for the remainder. You can do a normal, or you can just do a masked vector operation, or you can also do some scalar loop, which is just using sequential scalar code for the remainder of the loop. And you can see it is a very useful general vehicle that you want. There are, of course, more features in AVX 512, so it's pretty comprehensive. There are embedded broadcasts and masking. Embedded means, to give you an idea what an instruction actually is. An instruction is a collection of bits that enables the CPU to actually know what instruction it should execute. You know, on x86 general purpose instructions are varying in size. You heard that against RISC, and you know what that means. But with AVX 512, I think most of the instructions have, in a basic form, they have the unified or a single length or size. But the prefix or the instruction encoding itself can also contain operands. It's not just the case that you need operands always to be registers or from memory, but the instruction set also allows you to embed some of the operands into the instruction itself. It's sometimes useful, sometimes not. We have seen instruction set that just died because of that. The